Welcome back to the course LTE System Overview. Now we will talk about the configuration of the so-called cyclic prefix. As we already heard, in OFDMA we have the advantage that it is very stable against multipath propagation because we include a so-called cyclic prefix. This means that we copy part of the transmitted symbol to the front and therefore are stable against this multipath propagation. Now we have the possibility in LTE to use two different cyclic prefixes. They differ in length. So one symbol in LTE is 66.7 microseconds in length. So that 7 symbols in total sum up to this 1/2 millisecond, which makes up one time slot in LTE. And 14 of the symbols then make up 1 millisecond, so one subframe. If we use the normal cyclic prefix, this is the truth. And the cyclic prefix has a certain length, we will see in the next slide. For larger cells, where multipath propagation might be more problematic, we can have a so-called extended cyclic prefix. This means we have a longer cyclic prefix, but thereby we can only transmit 6 symbols within 1/2 millisecond. So here we have an overview with the normal cyclic prefix. One cyclic prefix has a certain length, 160 or 144 of these basic time intervals, so 32 nanoseconds times 160 is something around 5 microseconds. If we would need, or if we would take the extended cyclic prefix, it is more than 3 times as long, meaning that it is around 15 microseconds, and this means it is 10 microseconds longer. So in total, from the 7th symbol, we take it for the other 6 to extend the cyclic prefix. One symbol divided by 7 or divided by 6 is around 10 microseconds, and this means we can elongate our cyclic prefix by 10 microseconds, roughly 10 microseconds per symbol. There is also the possibility to have some multicast broadcast scenario, then we would be able to have an even longer extended cyclic prefix, but this is not part of this course today. So now we know about FDD and TDD frame structure. We also know that there are 2 different cyclic prefixes, and now we can see how the air interface in LTE is structured in reality. So here we see in the red line one so-called resource block. The resource block is made up of 12 subcarriers, 12 OFDM subcarriers in the frequency domain, and 7 symbols in the time domain, as we already heard. So one OFDM time slot or one LTE time slot is 7 symbols. We also already heard that one scheduler will always schedule 2 of those resource blocks because it will always schedule 1 millisecond in total. So what we also already heard is that we have a flexible bandwidth in LTE cells from 1.4 megahertz up to 20 megahertz. If we now think about the OFDM subcarriers, which have a bandwidth of 15 kilohertz, times 12 subcarriers, we have a bandwidth of 180 kilohertz per resource block. And this means that in the smallest bandwidth with 1.4 megahertz, we can only have 6 subcarriers in the frequency domain. With the larger ones, 3, 5, 10, 15, and 20 megahertz, we can have more resource blocks in the frequency domain. And with the largest ones, we have 100 resource blocks. And this means 1,200 subcarriers. We have to organize our subcarriers in resource blocks because if every subcarrier would be scheduled as sole resource, the calculation would be very complicated. Also, the scheduling would be very complicated, and we would have a lot of signaling over the air interface, and this should be saved. So this means that we always schedule resource blocks, and even sometimes we always have to schedule more than one resource block at once. So the one symbol, which is defined by 66.7 microseconds and 15 kilohertz is called a resource element. One resource block is 12 resource elements or 12 subcarriers in the frequency domain and 7 symbols in the time domain. So in the end, it ends up with 84 resource elements. Then we will also see that there is a so-called control channel. The control channel is made up by the first 1, 2, or 3 symbols of every second resource block. And in this control channel, our resource elements are put together to so-called control channel elements. So here, the signaling is also transported directly at the normal frequency resources over the air. So if we think about what we already learned, here we have the radio frame with 10 milliseconds divided into 10 subframes, which is 1 millisecond in length. This subframe again is divided into 2 time slots, and each of these time slots carries resource blocks, between 6 and 100 resource blocks, depending on the frequency bandwidth that we have in our cell. This means that we, as already said, have between either 6 or 15 or 25 or 50 or 75 or 100 resource blocks available in our LTE cells. So far to the physical structure of the air interface. Thank you for watching.